Hello, in this video I'm going to go over some tips and show you how to solve these two questions that involve gravity and the laws of motion. All right, so number one, we have three parts, A, B, and C. In part A, we're asked for a value of weight. Okay, so that's what we'll be solving for. In part B, we're asked for, I believe it's going to be weight again. Yep, so what is their weight? Again, all right. And in part C, how much would they weigh on a particular, somewhere else. So every single time it's going to be weight. Same measurement. Weight is a force. So we're going to be finding weight in newtons each time. Okay. All right. So in the first case, how much do they weigh on Earth? For that one, we have a very straightforward formula because gravitational force on the surface of Earth is just m times g, where g is a known value of gravitational acceleration. Everything falls at the same rate on Earth, and that rate is 9.80 meters per second squared. Okay, the value of mass is 65 kilograms. All right, as we can see here, that's one of the values that we'll plug in, a known value. Okay, and this will give us our answer right there in newtons. Okay. Now, part B, we have to use a different equation. We're going to use a different equation for gravitational force. I'll denote the difference by using a lowercase or uppercase big G opposed to a lowercase. This one has a different constant, uppercase G, and is a fraction of some mass times the mass of the planet that you're standing on. And in the case of part B, that planet is going to be like Earth, okay? And then there's some differences. All right, and then underneath is going to be the radius of that planet, so the radius of Earth, okay? So that is how you find gravitational force as opposed to finding gravitational force near the surface of Earth. In other words, this is a general formula that you can always use, okay? In fact, the value of G comes from using this formula, okay? This number 9.8 comes from solving this formula using Newton's second law, okay? All right. So what do you actually do in part B? Because if you were to plug in the mass of Earth and the radius of Earth, you would get a gravitational force that is exactly equal to part A, okay? So let me note that. All right. With these values, so the mass of Earth and the radius of the Earth, okay, the actual values. Oh, yeah, an important thing is missing. I forgot to square the radius of Earth in the denominator. And it is absolutely a squared function, okay? All right, so with that fixed, I was saying, so with these values, the gravitational force will be the same as your answer to part A, just right above, the one that was a straightforward calculation. Okay, so take note of that. But that's not what we're doing in B. We're not just solving this for the same number a different way. We're instead going to look at a different planet that's 5 times Earth's mass. All right, so that's one of our given values. So 5 times Earth's mass, but only half its diameter, okay? Half diameter also means half radius. Radius is what's shown in the formula. So if we go back, then the planet that you're given has a mass, big M, we'll just call it, that is 5 times the mass of Earth. Okay, and it's got a radius, so it's more massive but much smaller, or so it's a very dense planet. Okay, the radius is half of Earth. So what you will do is you will think of this formula instead of being specifically, so the universal force law, as it's called, instead of being specifically for the mass of Earth and the radius of Earth, we'll erase those subscripts and just say, okay, well now we're using this formula in general for any planet. In this case, the particular numbers are going to be 5 times the mass of Earth and 1/2 the radius of Earth. Okay, you'll plug those numbers in. Okay, you're expected to look them up, and then you will be able to calculate the force of newtons. Okay, it will absolutely, the answer you get should be larger than the weight on Earth. Okay, so answer will be larger than A, because this dense planet would make everyone have a heavier weight. Everyone would feel heavier. They'd be heavier. They'd be pulled down more. All right. Then in part C, it's going to be, in terms of being pulled down more, part C is the opposite. because Ganymede is a small moon. So, or rather, it's a large moon by any standard. It is a very, very large moon, but it's small compared to planets. So gravity should be much less than gravitational force on Earth. So you can definitely find out what those numbers are, and you'll have a smaller weight, maybe comparable to the weight on Earth Moon, which is 1/6 that on the surface of Earth. You weigh 1/6 as much on the moon, and you can actually find that number, that 1/6, by doing a calculation like this and putting in the mass and the radius of the moon. Okay, so we'll stop there. I'll make a second video for the second question. Yeah, so number 2. So thank you so much for watching this one. I hope it has been helpful.